Welcome to Transmission Podcast. I'm Cecilia Lynn Jacobs. I'm an actor in Transmission, a distributed reality mixed media podcast and performance series. This podcast speculates on the possibility of life on Proxima b, the closest planet outside of our solar system that has the potential to support life, and whether civilizations like our own could live there. What if we received their television and radio broadcasts? How would we listen in? Could we translate them? How could we communicate back? You may be wondering why I'm hosting a podcast about space exploration and the search for alien life. One of our goals with this project is to root our speculative story firmly in laws that govern our place in the universe. We have sought out dozens of brilliant scientists and people who are thinking deeply about space, probing the boundaries of our understanding. We have found that the facts are so much more interesting than anything we could invent, and so we wanted to share that with you. This podcast will be released from April until July 2017 while we prepare for the premiere of Transmission at the Edinburgh Fringe Festival in August. In Transmission, two brilliant sisters are selected to lead an interstellar mission to meet intelligent extraterrestrial life, but one decides to go and the other decides to stay. How can you let go of the only home you know, and the only planet we know supports human life? What is loneliness in a universe in which we know we aren't alone? Learn more about our team and upcoming performances at luxaterra.com and find us on Facebook and Twitter at Luxaterra. That's Luxaterra. Transmission is a production of Toaster Lab in Canada and is a fiscally sponsored project of Fractured Atlas in the United States. Welcome to Transmission Podcast. I'm your host, Cecilia Lynn Jacobs. This is our first episode, and we're talking about listening to space. When we think about listening, we usually think about something like this. But sound is not the only way that we can find out what is happening in our universe. We spoke with a number of astronomers and others involved in space research to discover the many ways that we listen to space.
I'm Pippa Goldschmidt. I'm a writer based in Edinburgh in Scotland. I used to be an astronomer. I used to do research with various telescopes into distant galaxies, try and work out how galaxies formed and evolved and how they formed black holes in them. I gave up academia some years ago and then I joined the UK government where I worked, amongst other areas, in space policy.
Pippa spoke to us about what listening means to her. And it turns out listening might be a misnomer.
So I tended to look at objects at different wavelengths with different types of telescopes. Probably the easiest to understand is using a sort of straightforward optical telescope. And in fact, one of the ones that I used was actually a bit like a camera, a large camera that did surveys of the night sky to look for objects called quasars, which are galaxies thought to have black holes in the middle. And at that time were thought to be very rare objects. So we took these images at optical wavelengths, which is the sort of wavelength that we're used to seeing with our ordinary human eyes. But I also used to use telescopes that worked at different wavelengths, radio wavelengths. And that's slightly confusing because it does sound like we are listening. And in fact, we weren't. We were simply looking at electromagnetic radiation, so like light radiation, but at much longer wavelengths.
Everything we did in astronomy was just measuring light from objects. I mean, the big thing that's changed is now we've actually measured gravitational waves from a few objects too. Two merging stars forming a black hole. But before that, and still 99.9% of astronomy is just measuring light from objects. Now, there is a huge range of different wavelengths you can look at, and there's a huge range of different techniques you can use. So now we are working along the whole electromagnetic spectrum from kilometer or meter length radio waves all the way up to X-rays and gamma rays. So in terms of listening to space, that's usually when you're thinking of radio astronomy. And I think that's just our association with radio.
That's Dr. Beth Biller at the Royal Observatory at the University of Edinburgh. We spoke to Beth about how we might observe another world, specifically an exoplanet, or an Earth-like planet in another solar system.
And in terms of SETI, we think of it as listening because we have made the assumption that, like we've communicated with radio, that another civilization would do something similar. In terms of astronomy, though, there's really, a wide range of different characterization you would do at different wavelengths. So there's simply imaging, which you can do in a fairly straightforward way from infrared out to about UV. So just making an image like you would with a digital camera. And so that can be useful. So let's say you were looking at a galaxy and you wanted to study the structure of that galaxy. You might just take an image and look at the structure. So that's one thing you can do. You can also look at spectra. So the way you would do this is using one of those, something similar to the grading that you might have used in primary school, which disperses the light, or a prism, right? But you're basically just making a rainbow with your light. So instead of looking at one wavelength or a discrete chunk of wavelengths, you're looking at different wavelengths separately. And so then you can look for structure in that spectrum. So we mentioned spectral lines earlier. So for instance, in the atmosphere of a star, you might have an atom that's absorbing light at a specific wavelength. And because it absorbs that light, you have a dark line in your spectrum. Spectroscopy is particularly powerful, at least for my field, in terms of exoplanets. It's what lets you know the compositions of the objects that you're looking at by looking for where those spectral lines are.
However, there are significant hurdles to observing these other planets. We spoke to Dr. Dan Tamayo at the Canadian Institute for Theoretical Astrophysics about the difficulties in studying exoplanets.
A lot of the richness in astronomy, what we know about stuff that's out there in the galaxy, comes from the fact that we can get lots of information, not just from the visible light that we see, but wavelengths across the electromagnetic spectrum. But we are sort of in this funny situation in our position on Earth, in that the atmosphere does not let most of those through. So, visible light can get through. That's probably, that's why our eyes evolved to see it. But then everything else basically is opaque until you get to the radio. The huge problem with exoplanets is that exoplanets, and specifically like rocky planets like Earth that are really small, they put out or reflect almost no light compared to the star, right? Like you're looking for a Christmas light, right next to an enormous floodlight. It's very difficult to just pick out that light.
Electromagnetic waves aren't the only option we have for listening to space. Dr. Avi Loeb of Harvard and Breakthrough Initiatives explains that we can now also observe gravitational waves.
Astronomy was involved in the detection of electromagnetic waves, this light that is produced by stars, produced by other types of sources, including black holes. But this is for the first time a detection of another type of waves, gravitational waves, which are basically ripples in space and time. You can think of it as space itself being dynamic quantity in Einstein's theory of gravity. So you can excite waves in space and time, and they propagate at the speed of light. The strongest source of gravitational waves would be a black hole because it's the most compact object that we can envision. And so when two black holes collide, you generate the strongest waves that you can. And that's the type of signal that we detected. But you can imagine other sources of gravitational waves that are not black holes. People over the years thought about speculative ideas like cosmic strings. So these are, they look sort of like a spaghetti, and they are condensed structures of energy that could be produced in the early universe. And if those exist, they could also produce gravitational waves. We could imagine gravitational waves coming from phase transitions in the early universe.
The way to think about listening into space is going to be to communicate with the electromagnetic spectrum, so communicate in light or radio waves or something like that. That's far easier to make and far easier to detect. So that's what people usually think of, I think, when they think of looking at the universe.
That's Dr. Aaron Zimmerman from the Canadian Institute for Theoretical Astrophysics.
So when I think of listening to space, I often think about gravitational waves. It's kind of a cute fact that when two black holes with masses above but comparable to our sun merge with each other, the gravitational wave signal we can hope to detect on Earth is actually in the audio band. So it's at 1,000 hertz or so. And so if you were able to detect these minute forces and convert them into a digital signal, you could listen to it with your ears.
So gravitational waves quite literally sound as cool as they are. And listening doesn't stop there. In fact, sound played an important factor in many early space observations. Dr. Katie Garcia-Sage, who researches space plasma, told us about the importance of sound in her work and how the telephone might have been one of the first places we heard space.
I thought that's a really neat question because historically, one of the ways that people knew about plasma in space was from listening to it. It turns out that what we think of as empty space is not actually empty at all. It's filled with magnetic fields and ions and electrons and electrical currents and flows of plasmas of these sort of ions and electrons moving together with magnetic fields. And whenever people would listen to sort of radio frequencies on telephone lines and things like that, then they could actually hear noises that they knew weren't coming from the Earth. Is coming from plasma waves that were traveling along Earth's magnetic field. And so, now most of what we do to observe them is using spacecraft data, but all of these waves have names that are descriptive of the sounds they sound like. There are things like whistler waves that sound like a falling tone, like a whistle. Chorus waves that sound like a chorus of birds. Hiss waves, and even lion roars that all have these sounds because one of the biggest ways that people studied them before using spacecraft to do it was by listening to them.
So we know that there is a lot that we can observe in space and that it literally makes a lot of noise, but it is still very difficult to study objects in space that aren't very massive and don't reflect substantial amounts of light. We asked Dr. Beth Biller about the difficulties of peering in on exoplanets.
The technique that you're using basically has to work with really, really massive things because of the distance that we're working with most of the time. Is that about correct, or am I missing some subtleties?
There are two big issues you have to overcome if you want to directly image a planet. The first is you have to resolve something very close to the star. It's kind of like, in terms of resolution, it'd be like if you were looking at, in terms of contrast, if you were looking at a firefly next to a lighthouse, and you're in Edinburgh and your firefly and your lighthouse are in Dublin. So that's the technical problem in terms of resolution, in terms of the contrast, also how bright the planet is versus the star. We actually have ways to get to those sorts of contrasts and resolutions. The main thing that prevents us from getting that sort of resolution is the atmosphere, right? So it's very turbulent. If you have a telescope, the best resolution of that telescope is proportional to the wavelength of the light that you're looking at, divided by the diameter of the telescope. So a bigger telescope gives you, theoretically, better resolution. But if you're working from the ground, the atmosphere prevents you from getting to that best resolution. It basically blurs everything out because of its turbulence. So if you ever see a star twinkling, that's what's going on. It's called seeing.
So if it's this tricky to even detect a planet, what does this mean for extraterrestrial detection? When we return, how would we find those little green men? Stay close. Welcome back. We've been discussing how we listen